NoSQL series. In this video, we'll be discussing the important topics of third module. So third module comprises of two chapters here. So the first one is map reduce and the second one is key value databases. If you're new to my channel, do check out the NoSQL playlist where I've uploaded module-wise videos for all the modules and I've covered all the important topics. And do check out the important questions video also because we have discussed all the important questions from exam perspective. And if you're new to my channel, do subscribe so that you don't miss out any of the updates. So coming back to module 3, out of these two chapters, I would say key value database is very easy and definitely a question would be asked from this for 10 marks and map reduce for 10 marks. So under key value databases, there are only three topics. Okay. So let's cover key value databases first. So a question could be asked like what are key value stores? What are the popular key value databases? How will we store the data in a single bucket of key value store? So for that, this is the answer. So we'll understand how key value databases or how key value stores actually work. So key value store, we know key and value. So key comprises of some data and in key comprises of a parameter and in the value we store the actual value, right? So the key value store is a NoSQL database that functions like a simple hash table. So in simple hash table, we will store the data in key value pairs. Okay, so key value store will enable extremely fast lookup. So it is very easy to find data from this key value pair or key value store because if you know the key, you can easily get the value right. So that's how the querying becomes very fast here because it is very easier here. So thereby it is a popular choice for scenarios where high performance and scalability are essential. So key value stores simplify the database interactions by providing straightforward API for basic three operations. So those three operations are, first one is get. Get means we are retrieving a value using the key. Then we have put. Put means we are storing or updating a value which is associated to this particular key. Next, delete means we are deleting this entire key value pair. Okay. So looking at the data structure. So the value in the key value store is a opaque blob, BLOB, that is binary large object. Binary large object means the database can store without needing to interpret its content. Okay, so the responsibility of understanding and managing the structure completely depends on the application. So if you look at the primary key access, the key value stores operate purely on the primary keys. So they make use of primary keys, thereby allowing efficient direct access to the data and thereby making changes accordingly. So in resulting in low latency operations. Stores that are horizontally scalable. So horizontal scalability is one of the important characteristics of key value stores. If we are horizontally scaling it, it means we can handle a large amount of data here. So large amount of data could be stored and accessed easily. Looking at the popular key value stores. So the first one is React. So it organizes the data or the keys into buckets. So these buckets will act as flat namespaces for grouping the related keys or related data. Then next we have is Redis. So it extends the functionality of traditional key value stores by supporting the advanced data types like list, set, hash, thereby enabling broad range of user access and use cases. Next we have is meme cached. So it is optimized for caching by storing the key value pairs in memory. So if you are storing the key value pairs in memory, it becomes very easy to access it, right? So next we have is Amazon DynamoDB, Amazon Dynamo database, which offers a fully managed cloud-based key value store with additional features like secondary indexes and fine-grained access control. So if they ask about popular key value databases, you can mention these four. Okay. Next, moving on further, we have React supports creating domain bucket. So speaking about React, it supports creating domain buckets, which are the namespaces for keys that group the related data. So we can group all the related data into this bucket. Okay, so these are called as domain buckets. So by domain we can understand, right? Domain means all the similar or related data would be grouped. So they are grouped and thrown away in a storage container, that is like a bucket. Okay, so domain buckets are helpful for handling the serialization and deserialization process, thereby storing, that is storing and removing becomes very easier here. Next, domain buckets will separate the data by type, ensuring that no collision is happening, and it also ensures that easy management of related data keys are happening here. Along with that, even the efficiency to retrieve the data is also higher because it will only fetch or it will only retrieve the necessary data instead of fetching the entire blob. So here we have figure 8.1, which is storing all the data in single bucket. So here we have the user profile, session data, shopping cart, cart items, everything has been stored in one single bucket itself, right? If we speak about the advantages, it is very simple, right? So all data is stored in single bucket without any requirement of complex schema. Next, it is faster lookup. Faster lookup means with a single key we can retrieve the entire data, we can retrieve all the relevant data here. But speaking about the key conflicts here, first one is, if we are storing different types of data here, it might lead to collisions, right? And along with that, if I am updating one data, if I am updating shopping cart, then the entire bucket has to be updated, right? The entire bucket has to be rewritten, so thereby it will again lead to inefficiency. So to overcome this, we had the second method, so that is improved key design for segmentation in a segmented data in a single bucket. So here, to address the challenges of this, the different aggregates in a single bucket, we can modify the key design to segment the data effectively. So here we are segmenting. Suppose the user profiles will contain the separate user profile values, and the shopping cart will contain the shopping cart values, and the user preferences will contain the user preferences value. So this way we are appending a descriptive suffix here firstly, that is, it could be the user profile or shopping cart. All these are prefixes to the key. So by this design, it will allow us to retrieve specific data without fetching the unrelated aggregates. So thereby it will also improve the readability and efficiency aspect. So this was about both the figures. It will reduce the conflicts and optimize, separate them in domain buckets, append descriptive data. Here we are modifying the key design into segmented data efficiently. So here I have just mentioned about the figures. In exam, if they ask about key value stores, then you have to write all these points, and then these two figures are very important. If they ask anything related to bucket, this is the first condition. To overcome the drawbacks, we came up with this. This is the second diagram which you have to draw and explain. Looking at the advanced features of key value stores. So Redis as a data structure store. So Redis extends the support, it extends the concept of key value storage by supporting multiple advanced data types. For example, lists. So lists are used for ordered collections of items like users, recent activity, and all of that. Next, we have sets. Sets are used to store the unique elements, and we can perform operations like union, intersection on sets, right? Next, we have hash. So hash will store key value pairs within a key. So hash will store key value pair within a key, thereby making it ideal for representing objects with multiple fields. So in such conditions, you can use one key to represent one object, one key value pair, and another key to represent another key value pair. Thereby here, if you see, we are storing multiple objects within multiple fields here, right? So yeah, these were the features. Next, we have key value store features. So key value stores are a part of NoSQL database family. So it offers distinct features compared to the traditional RDBMS. So this is understood, naturally understood, right? So it will offer certain extra features, right? So understanding these features are very important for designing the applications that effectively utilize the strength of key value stores while addressing the potential limitations. So there are 5 features here, 1, 2, 3, 4, 5. Out of these 5 features, we will cover all the aspects, all the strengths of key value stores. Along with that, we'll also address the potential limitations. So this question could be asked for 10 marks, guys. Straight away, it could be asked for 10 marks. And this question again could be asked for 10 marks. So let's look into the features one by one. Okay, so the first one which we'll encounter is consistency. So consistency means it applies to all operations on a single key, as these operations like get, put, delete are straightforward and atomic. So we know that in key value pairs or in key value stores, all the operations are atomic. So on one key or on one value, we'll be performing the operations. Either it could be get, delete, or put. So it is very important to maintain consistency when it comes to these single keys, right? So we'll look into the eventual consistency in distributed systems like React. So the eventual consistency model is used. This model is used to update the updates to the key may take time to reach all the modules. That is, eventual consistency model means updates to the key will take some time to propagate to all the nodes. So conflicts can occur if multiple nodes are holding different versions of the same key, right? So React will resolve this problem using two methods. First one is last write wins. Last write wins means whoever has the newest update will override the older update. Next we have is client side resolution. Client side conflict resolution means all the conflicting values are sent to the client, and client will decide which value is the correct version or which value should be the correct version. Okay. Next we have what is the bucket configuration. So buckets are the namespaces for the keys that help to reduce the key conflicts or key collisions. So while creating a bucket, we have to define the consistency parameters like W. W means the number of nodes that are required to acknowledge a write before it is considered as successful. We have studied W, R, all these topics in the second module, right? So the same thing here. Next, R. R means number of nodes which are required to respond to a read operation. Next, we have allow siblings. Allow siblings will allow or disallow conflict versions. Conflict versions means conflict siblings for a given key. So this was about the consistency. Next, moving on, we have transactions. So under transactions, we know key value do not provide asset properties. Key value stores don't provide the asset properties like atomicity, consistency, isolation, durability, which are guaranteed in the traditional database management systems. But then these key value stores have a alternative. Okay, so this alternative is lightweight transactional method to ensure some degree of reliability. So we'll look into them. So quorum is used for write and read operations in React. So we have studied quorum in the second module. So we know write quorum is it will specify minimum number of nodes which are required uh, to confirm that a write operation has done successfully. Then read operation means read quorum means it tells about minimum number of nodes which are required to confirm that read operation has happened. Next we have n. N will tell the total number of replicas of a key which is created. So cluster tolerance. Cluster tolerance means the tolerance up to which the nodes can handle during the failing of write operations. It is n minus w. Suppose I take n is equal to 5. That is, if I have 5 nodes which are replicated and w is equal to 3, that is, I need 3 nodes to confirm the write operation has happened properly or not. What is the tolerance here? Tolerance is n minus w. That is 2. I can say that 2 nodes that the cluster can tolerate 2 nodes which are failing during the write condition. So users can achieve level of reliability in write success and data availability. Again, with some reliability, we can achieve the write success and data availability aspect. Next, we have query features. So key value stores support retrieval by key only. So we can retrieve the data by key only. So this way, it makes querying fast, but it is limited. So what are the challenges? So first one is lack of secondary index. So we cannot search based on other alternates or other attributes of the value. So if we have to find this value, suppose I am writing ABC, then its corresponding key only I should search. So there is limited lack of secondary indexes happening here. Next, I have limited support for ad hoc queries. That is, debugging and analytics will require predefined key design strategies. So thereby, it is very limited support is provided here. So React addresses these query limitations by providing indexing features like this Lucene that allows searching within the values. So key design becomes very crucial as application must generate meaningful keys for efficient data retrieval. So this constraint makes key value stores best for querying the predictable applications. It could be the session storage or shopping carts. In such applications, we can implement our key value stores, right? Next, we have what is the structure of data. So the value part of key value pair can store blob, that is binary large object. Binary large object, along with that, it can also store the JSON format. It can store the XML format. It can store text, blob, all these things, right? So it further shifts the responsibility of data interpretation to client application. We have seen this previously also. The responsibility of interpreting the data or understanding the data goes on to the client application. So for example, React allows users to specify the data types in request via content type headers. So in React, we make use of content type headers, which will simplify the decentralization process. But even though it is simplified, it does not impact the overall database storage as binary large object. Next, we have a scaling. So scaling, we have sharding or partitioning data across multiple nodes based on the keys will enable the key value store to store success to scale horizontally. If you are scaling horizontally, we can store large amount of data. So first we have is key based sharding. So here the key will determine which node stores the data. For example, key starting with F are stored in node 1, key starting with A are stored in node 2 accordingly. Next we have is replication. So data is replicated across multiple nodes to ensure reliability is met. Next we have If a node is responsible for certain key fails, data within those nodes will also become unavailable till the node is retrieved. So key value store uses the replication and settings of cap theorem to offer trade-offs between the consistency, availability, and partition tolerance. So this was about the features. Next, we'll look into what are the use cases. So key value stores will offer a simple and efficient storage model suitable for applications where data can be represented as individual items within the unique keys. So this question is again a 5-mark question, and here when not to use is again a 5-mark question. So first one is storage session and info. That is, each web session is the use case here is each web session is assigned a unique session ID. In such conditions, we can store this session uniquely, right? So advantage is here is we can retrieve these data in a very efficient manner. Retrieval is very fast, and storing it in a single put or get request is ideal for storing the session data. Examples could be the memcached or React memcached or React can be used here, where they will offer enhanced availability for session consistency across multiple requests. Next, we have is user profiles and preferences. So here, user specific settings like language, time zone, or access permissions are all specified here. So all user profile data can be stored in a single object, allowing quick retrieval of this of the purposes or the preferences of users. So the profile can be stored with a unique user ID, like how it is stored in Twitter, Facebook, and all, right? Making it simple to access the user settings with just one single get. Next, we have shopping cart data. So shopping carts tied to individual users can across sessions, browsers, and devices. All the cart information is stored under a unique session key or a unique user ID key. So this will ensure high availability. For example, a React cluster which maintains availability and fault tolerance makes it suitable for this particular application. And when not to use the key stores. While key value stores are effective for certain types of data storage, they are not ideal for all the scenarios. First one is relationships among data. That is, the complex relationships or associations between the data items are difficult to handle in the key value stores. Next, we have is querying by data. So if you are trying to query by by referring the the value part, it becomes very difficult, right? Next we have is operation by set. So if you are trying to operate certain sets of data, then again it becomes difficult. It is not suitable for such conditions. So these were the drawbacks or when not to use about the key value stores. So both of these could be asked for 5 marks, or it could be clubbed with other questions also. So this was all about key value stores. We have this first topic, which is 10-mark question, that is the basic introduction about key value stores. Next we have the features. Again, it could be asked for 10 marks. Next we have is when to use and when not to use. That's it. Next, we'll look into map reduce. Map reduce topic is slightly trickier compared to key value stores, but then it's okay, we'll cover map reduce also. So map reduce is a programming framework which is designed to process and analyze large data sets across clusters of machines. So we know that a big large chunk of data is divided into different clusters. So these clusters are different parts, and these parts would be further processed by making use of clusters of machines. So by map reduce, we can achieve scalability and fault tolerance by dividing the task into smaller chunks and parallelly running them on multiple nodes or multiple servers. So Hadoop is the notable open source implementation which is well known for map reduce technique. So under map reduce, there are two processes or two stages. First one is map. Map means we are transforming the input data into key value pairs. Okay. Next, reduce. Reduce means we are aggregating or combining, aggregate or process the key value pairs which are generated by maps to get the final result. In reduce part, we are performing the operation. In map part, we are just splitting it up into key value pairs. So looking at the components now. So what are the components which are important for map reduce operation to take place? First one is map function. Map function will take input, that is a single record. It could be order or a document or anything. And what would be the output? Input would be the single document, and output would be the key value pairs which are generated. So it will ensure that each map task processes the data independently, ensuring all parallel execution is happening. Next we have is shuffle or sort. So this Shuffle or sort, the framework groups all key value pairs by their key and moves them into proper reduce task. So here it will ensure that all values which are associated to the same key are sent to the same reducer. So all the values of same key, all the key value pairs which are having same key are clubbed together, or they are shuffled and sorted together. Next we have is reduce function. In reduce function, input would be a key and a collection of all the values that are associated with the key. After shuffle and sort, we will go to the reduce function, right? Output would be the single aggregate result per data per key, right? So example of reduction is summarizing the values, counting occurrences, finding averages. These are just the examples, okay? And what about execution and framework? So execution framework will manage the task scheduling, data distribution, fault tolerance, and resource utilization. If we look at the steps, first step is input splitting. That is, I'm dividing the given input into smaller chunks. So these chunks are processed in parallel by different nodes. In map phase, I am taking each chunk and processing it independently by the map function. So I will give out the key value pairs as intermediate results here. In shuffle or sort, I'm grouping all the values by their keys and transforming the group data into reduced nodes. So in reduced nodes, I'm processing each key data and its associated values, and I'll give out the final output. Final output would be the output whichever I want. Okay. So next we have this question could be asked for 10 marks. That is basic map reduce. So here you have to describe the entire whatever I have explained above. So basic components, you can speak about the stages, introduction, and then you have to write from this part. So we have a scenario of sales analysis for the product revenue. The data set given here comprises of orders which has multiple line items like product ID, quantities, and prices. And our objective is to compute the total revenue for each product over last 7 days. So we'll look into this figure, okay? So this figure has the ID, customer ID, line items, and shipping and payment details. So this entire thing is one aggregate, right? So this is the order aggregate which I have, and output I want is key value pairs, right? So here if you see, let's take this line item. This line item is split with the price here and quantity here. So here I am deducing the key value pairs in which key will be the product ID and the value would be the quantity and the price. Here it is product ID, right? It is product name. This is product name, right? So I'm reducing it with the product name, and here I have the value, product name value, product name value. So this is how I am generating from a given aggregate. I am generating key value pairs. So here each map task will operate independently. So processing one at a time, which will ensure that parallelism is achieved. So this was about the basic basic map function for read records from the database and emitting the key value pairs. So our first operation is done. That is, from the given aggregate we have deduced the key value pairs. That is, in the map function is done now. Next I have to look into the reduce part now. So under reduce part, input would be here. Input would be the key value pairs from map phase. So if you see here, for this particular line item, there was price and quantity, right? So this was $26 and $8. So if you check out here, $26, $8 is there, but then along with that there are extra entities here also. So as we saw previously, under reduce step, all the data which has the similar key are aggregated here. They all are combined here, right? They all are taken into consideration here. So reduce function will take several key value pairs with the same key and aggregates them into one. So here I am taking the entirely whichever values have the same key are written here. So here I have just taken, here there are just 3 records, but there could be thousands of records here, right? So thousands of line items could be there, and there could be chances that this PUERH is repeated multiple times, right? So all such multiple things with PUREH as key are clubbed together, are taken together, and reduce operation is being performed on it. So this reduce operation will combine all the values here from a single key to produce the final aggregated output. So here if we see, it is doing the addition operation. So 8 plus 12 plus 14, it is adding all the quantities and adding all the prices. So here it is, here we are getting one aggregate for one particular key. So here we are generating key with value as an aggregate for all the value pairs in the initial aggregate function. So this was about the key value pairs, and so it is very simple, guys. So firstly we are performing from a given output, that is from a given aggregate, we are splitting it up depending on the keys and the similar values. So here we get the key value pairs, keys would be the line items and values would be the price and quantity. In exam, if you don't remember this, just take a random example and draw the diagram, but content has to be same. Okay, next here we have the key value pairs, and we are combining all the similar values which are having similar keys and reducing it with using one function. Here the function could be aggregation or addition. So processing is done here, and after that I am getting the final output for the given key, right? So here let's quickly write the advantages. So the first advantage is scalability. That is, I can process a large chunk of data across multiple clusters, across large clusters. So thereby it is very scalable. Next we have parallelism. So parallel computing is supported here because I'm breaking large chunk of tasks into small parts and I'm executing these small parts or chunks together. Next I have is fault tolerance. So if a node fails, the frame will reassign the task to another node and another node will execute the functionality. Scalability and flexibility both are nearly same. If it is scalable, it is flexible, of course, because it is supporting thousands of bits of data to run in this process, right? So thereby it is efficient here. We'll now look into the next question, that is partitioning and combining in MapReduce. So this could be asked for 10 marks directly. It is there in the model paper also. So let's understand what partitioning and combining is. So partitioning and combining are the optimization techniques which will enhance the efficiency and scalability of MapReduce operations. So they'll address two challenges. First one is increasing parallelism, that is distributing the work among different or multiple reducers, right? And then reducing the data transfer, that is minimizing the amount of data which is sent across the network over map and reduce phases. So both these limitations could be addressed by making use of partitioning and combining operations. We'll understand what partitioning is first. In partitioning, we'll be dividing the output of map phase into smaller subsets or partitions which are dependent on the keys. So here each partition is processed separately by individual reducer. So here we have seen each entity is processed separately in the map phase, right? So as an extension in partition also, each and every partition would be processed separately. So looking at how partition works, firstly we make use of we map the output keys with assigned to partitions using the partition function. Partition function could be anything. It could be a hash function. Hash function might distribute the keys uniformly across the partition. So the keys in same partition are sent on the same reducer. Next we have parallel reducers. Here each reducer will process one partition. Each reducer will process one partition and it will enable multiple partitions to work simultaneously. So multiple partitions are reducing, multiple reducers are processing multiple partitions here, right? So this was about partition. In partition, we are simply taking the output keys and then partitioning it using a partition function. After partition function, these tiny partitions would be processed further by making use of reducers. So this is basic definition of partitioning. Next, coming to combining. So in combining function, we are combining, that is local aggregation step that will occur before the shuffle and sort phase. So here we are reducing the amount of intermediate data which is sent over the network by pre-aggregating the key value pairs. How does the combining work? First step is local aggregation. So here we make use of a combiner function which will process the map output on the same node where it was generated. On the same node, wherever it was generated, it has to be processed. Next, we are looking into data reduction. So in data reduction, we will be combining the multiple key value pairs for the same key having multiple values. We have seen this previously, right? So by doing this, we are reducing it into smaller pairs. Next we have is network efficiency. Network efficiency means by reducing the data where it was generated, that is locally itself, we are combining, the combiner will minimize the volume of data that has to be transferred to the other shuffle phase. That's how by making use of the combining, we can simplify the process, and not just that, the local aggregation, data reduction, and network efficiency are also met. Looking at the requirements for combining, first one is combinable reducers. So the combine function must have same structure as the reducer. For example, the input and output format should match. Next, if reducer output format differs, then a separate combining function must be implemented for it to execute. So looking at the workflow, first we have map. So in map phase, we will process the input data and generate key value pairs. We have seen this previously. After that, we'll do the local combining. Local combining means we are applying the combiner function to reduce the map output to the local node. After that, we'll do the partitioning. So here we'll divide the map output into partitions based on the keys. So here each partition would be given a specific reducer. After that, we are doing the shuffle and sort. So here we are transferring the data across from mappers to reducers, and we are grouping all values from the same key within the partition. Next, after that, in reduce, we are reducing the process, processing each and every partition and producing the final output, and final output we get at the end. So if you look at this figure, it explains all the steps. Okay. So first figure says the partitioning allows reduce functions to run in parallel on different keys. So here partitioning involves dividing the output of mappers into different groups based on their keys. So if you see here, we are reducing it firstly, right? So this dragon well, and the other these line items are reduced first, right? And after that, they are mapped here. So all the dragon well are mapped on one way, and here also we have dragon well, which is again combined here. So here we are partitioning based on the keys here, the line items here. Okay, and whichever line item has similar, whichever line items are similar, they are combined in the next step. So here I am doing partition step. So here each partition would be processed by a separate reducer, and it will enable multiple reducers to run together. After that, this process will ensure that all key values are associated with specific key here, and they are grouped together, and then they are sent to reduce operation. So here firstly I am doing the partitioning, and here I am doing the combining. Partitioning, combining, very simple guys. Dragon well is taken here, and here also dragon well is there, it is taken here. Along with that, there is this HOJICH, it is also written here, because this key and this key are combined together. And looking at this part, this PU and GN and PU, so PU, GN and PU, along with this GN, GN, PU are combined here. So the combination happens using different functions. Combiner function could be varying, it could be the hash function or any other function. Okay. So next, here we have the map, right? So a combiner is a mini reducer. Okay. So this mini reducer will aggregate the key value pairs locally on the mappers node before transmitting the data to the reducer. So by doing this, by summarizing values for the same key, the combiner will significantly reduce the volume of the data which has to be sent further. So this combiner which we have, this map which we have got here is further sent to the reducer part, right? So here we have the map part. So this map part has multiple entities. This PU, 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 and we have 1, 2, 3. We have 3 GEs and 1, 2, 3, 4, 5, and 5 PUs. So all these could be combined, right? So some logical function could be used here to combine these entities. So here I am combining in order to reduce the data which has to be sent to the reduce function. So if you check out the reduce function, only 2 entities are being sent. But then here, when we got the data here after partitioning, it was so many entities. It is reduced and combined to logical entities which are sent across the node. So by doing this, it will combine, or it will optimize the map reduce process by cutting down the redundant data movement here. After this, so there is one case where the combinable reducers are present here. In this case, if you check, we have dragon well, two dragon wells are there. So 1, 2. and then we have PU, 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 PU. 4 PUs are there. So here I've written 3. So this reduce function which counts how many unique customers customer orders are a particular is not combinable. So there could be situations where a scenario where a reducer cannot be used to combine the cannot be used to combine because of the differences between the input and output. So if you check the input and output, the number of uh, these line items which are involved are varying here, right? So the reducer's input does not match with the reducer's output, so thereby I cannot use combiner here. So a different combination strategy could be used here, like eliminating the duplicates and product customer pairs, further combining it and producing it. So this dragon and dragon are duplicates. I can eliminate one and give out one dragon and. Then we have this PU and AN and PU and B, PU and C and PU and D. So there are 1, 2, 3, 4. So 4 PU can be written here. Then GEN, and we have one GEN here. So one GEN I have written. Then I have HO. So there's one here. So I have written one here. So 1, 2, 3 and 4. Yeah, so here it has to be 4. Okay, PU for PUER it has to be 4. So at some times the combiner functions may not work properly. In such situations we have to come up with a new strategy, a new combining strategy for eliminating the duplicates. Okay, so this was all about the combining, partitioning and combining in MapReduce. Again, a very simple topic, guys. Just understand how it works. So from a given data I'm mapping it, firstly I'm partitioning it, and after that I am aggregating all the similar parts here, similar line items. After that, in the combination process, if the combinations are, if there is combinable reducers, then I am reducing it using some logical function. If not, then I have to deduce a new function here. So that's it, very simple. Moving on forward, we have composing the map reduce calculations. So again, map reduce calculations could be asked for 10 marks directly. So again, we have to explain this with a figure. So composing calculations in the MapReduce framework will involve structuring our computation to align with its constraints. So whatever computation we perform should align with the input data, output data, and all the constraints which are provided, right? So in order to compute the calculations also, we have to focus on how to break down the operations into independent maps and reduce tasks while obeying the rules here. So first is map. So under map we will operate on individual aggregates, and in reduce we will operate on key grouped operation, key grouped output from the map task. We'll look into what are the constraints and considerations we have to keep in mind. First one is single aggregate in map task. That is, a map task can process only one aggregate. That is, a map task will take only one aggregate function as input at a time, right? Next, it has to emit key value pairs as intermediate outputs. Next, we have a single key in reduce task. So a reduce task can process all the values which are associated in a single key. So all the values could be processed, but then it has to be associated to single key. We have seen this in the first topic itself. So after that, it will combine these values to provide the final output. For one key and one value would be generated, right? Next we have is composable calculations. That is, calculations must fit within the map and reduce framework. Operations like sum, count are composable as their intermediate result can be aggregated in the reduce phase. So this was about the composable calculations. First figure says uh, as to how to average can be computed by making use of map reduce by breaking down the calculations into composable parts. So here our challenge is averages are not composable. That is, we cannot combine averages of two groups directly to compute overall average, right? For example, if group 1 has average of 5 and for 10 items, and if group 2 has average of 7 for 20 items, combining these two averages, that is 5 plus 7 by 2, does not yield to the overall average of group 1 and group 2, right? To overcome this, we will make use of mapper phase and reducer phase. Okay, so in mapper phase, for each order we will emit the total quantity and a count of 1. For a product, let's say with an order of 4 units, we can emit the sum as 4 and count as 1. After that, in the reducer phase, we will combine the sums and the count for each key or each product. That is, add up the quantities for the product, sum, and number of orders, that is count. So we use these combined values to calculate the average. So this average would be total sum by total count. So here I am emitting pairs like sum and count for the individuals, and reducers are combining these pairs to calculate the average. Total quantity taking here, total quantity is 1200. Number of orders 10 plus 15, 25 is taken here. And next I have mean quantity. So you, as we saw, mean quantities cannot be summed together, right? That's why we get 60 plus 40 as 100, but then we are taking a mean of these two further, thereby getting 48 here. Average must be calculated from the combined sum and count here. So in order to calculate the mean quantity, again we have to take average and number of orders further. Okay. Next we have, when making a count, each map emits one which can be summed to get total. So our goal is to count the total occurrence of an item or key across all the nodes. So here for each item in the map phase, for each item we will emit count of 1. For example, occurrence of product is emitted as 1. In the reducer phase, we'll sum up all the counts which have been emitted by the map previously. For example, I take k. If k appears 3 times, then the map emit 3 ones, right? 1 1 1. So these all are summed together, yielding to a total count, right? So total I've got here. Number of orders 3 I've written here, and this mean quantity is by emitting how many times it has been emitted. All those things have been included here. Next, yeah, that's it. We have explained about 7.6 and 7.7. So combining map reduce calculations is slightly trickier. I'll just go through this again, and let's look into the 2 stages of map reduce example. Okay, so this pipes and filters model is beneficial when processing tasks involves multiple phases, each of which can be built upon the output of previous stage. So from stage 1 we are getting the input and then further processing it, thereby getting it in 2 stages. So in first stage we are calculating the aggregate monthly sales. It involves, to summarize the sales by product and month for each year. This stage involves firstly mapping. That is, I am mapping each input record or each sale to a key value pair where key will combine the year, month and product and the value that is sold. In reducing step, all the records with the same key, same product in the same month of same year are aggregated, summing up quantities. This gives the total sales for each product in each month. For example, sales record, the mapper might give output as keys. Key would be 2011 and it is 12 and the name, and the value here is quantity. Looking at the reducer will then aggregate the records to produce one record per product per month, such as for year 2011 month 12 product is this and quantity is this. Looking at the second stage, that is year on year comparison. In second stage, the output from the first stage is processed to compare the sales of each product in given month with previous year. So first we do the mapping, where each record is mapped and the mapper identifies whether it belongs to current year or previous year. After that we are doing the reducing process, that is reducer will merge the records for same product and month from both years. Thereby after combining those, I am calculating the average year, a percentage increase or decrease, and produce final record showing the comparison. For the same product, this in December 2011 and 2010, the reducer might produce. So if you see the product, this product name, month is 12, current quantity is this, prior quantity is this, current quantity, prior quantity have been compared here, and increases 20% that we can say. What are the benefits of using the 2-stage approach? First is parallelism, that is each map reduce task can be executed in parallel. So first stage can be executed, second stage can be executed, further we are comparing it. Reusability, that is I can make use of the data stored, reused, analyzed separately. Cluster suitability, final output are ideal for distributed storage, which enables quick data access for downstream processing. So by making use of tools like Apache Pig or Hive or Hadoop will further simplify this model by providing high level abstraction. Next we have reusable intermediate outputs. So these outputs from the map reduce can be stored as materialized views, thereby I can use them whenever I want the pre-computed output. Then we can optimize the query patterns. So we can build the materialized views which are based on the actual queries. They have speculative reuse, can be inefficient here. Next we have is language support. So it supports these languages which we have seen. Beyond NoSQL, it is Useful in many environments, not just SQL, as it is ideal for distributed processing on large data sets. Next, we have is cluster friendly. MapReduce is well used for handling large volumes of data across clusters, making it useful for data processing. So, after MapReduce, so here we have two comparisons of 2010 and 2011. So calculation broken down into two steps, which have been expanded into three figures. So the first figure here we can see. So we have product of 2011 and 2010. The name, year, month and quantity, name, year, month and quantity. Comparing these two, you are combining here with increase, additional attribute you are adding here. That what is the previous year's quantity, what is the existing quantity, and what is the increase. So if you, for example, we are creating records for monthly sales of a product here. So if you see 2011 12th month, 2011 12th month, 11 12th month, product is P here, product is P here, and here we have Dragonwell. It is 2011 12 26 11 12 44. So quantity is varying here, and quantity is varying here, right? So in that case, here we can see 2011 only combined. We are taking year is also same, month is also same, quantity we are aggregating it. And here on the Dragonwell also we are reducing it. The same thing has been written here. Okay. Next, the second stage mapper create base records for year on year comparison. In order to do the year on year comparison, previous year for both the quantities have been taken here and they are compared further. The reduction step in merge of incomplete records. So prior year was 0 and prior year was 0. Quantity is 0 here, quantity is 0 here, quantity is 1200 here, and quantity is 1000 here, sorry. So by taking an average increase, I'm specifying it here. So I would suggest you to go through this topic again in the notes, and because it is important, 10 marks. Next, moving on, we had this question in model question paper which was asked for 10 marks. So we'll look into this, how to solve this. Here they have all the details given, product, customer, price and customer ID are given. So we have to calculate total sales for each product. So the total sales for each product are calculated as total sales is equal to quantity into price. We have to multiply these two, right, to get the total sales of the product, right? So firstly, map function. So map function is responsible for transforming the input, this entire input, into key value pairs. So for calculating the key value pairs, key would be this product, and what would be the value? What value would be the total sales? In order to calculate the total sales, I have to multiply the quantity and the product, right? So that way, for this person, I'm calculating 8 into 24, 192. For Dragonwell, it is 12 into 24, 288. Then for this person, it is 20 into 80,600. For this person, again 5 into 15, 75. Dragonwell, it is 16 into 48, 748. So this is the intermediate output which I have got, that is key value pairs. Key would be this, and value would be the total product, that is 192. So intermediate key value pairs have been written here in Dragonwell, all the 5 quantities, all the 5 entities, right? After that, I'll do the shuffle and sort. So shuffle and sort is handled automatically by MapReduce framework. In this phase, the intermediate key value pairs are grouped by key, that is product name. After that, so we are initially we are grouping here, okay? So this P is being grouped. There was 192 as one record and 75 as one record. So those two have been grouped here. It goes the same with Dragonwell also. So for 288 there was one record here, and then for 766 there was one record. So both of this are grouped together. Now the data is grouped by product if we see, right? And we are ready for the reduction operation. In reduce operation, we take the intermediate key value pairs and aggregate them. In this case, the reduce function will sum the total sales. So for this P, we are adding these two. 192 plus 75 will give us the total sales. Total sales is 265 for P. 267. So I have written here 267. Next for Dragon. For Dragon also it is 288 plus 768. I get 1056. I have written 1056 here. Next for this G, it is 1600. So I have written 1600 as it is. So that's it. It is a very simple topic. Firstly, we are mapping it, and then we are doing the shuffle and sort, and after that we are doing the reduce function. So end of the third module. We have tried covering all the important topics of third module. If you have any doubts, do let me know in the comments, and do check out the other module videos also, right from module 1 to module 5. Everything is uploaded, Even the important question video is uploaded. If you have any doubts, do let me know in the comments. Subscribe to my channel. Thank you.